Welcome back. This is the final part of the Laplace transform. I would like to present different examples, process systems, mechanical systems, and electrical systems. And I will show through examples how can we get the transfer functions from the equations of the model. We start first with these process systems, which is composed by a simple tank with a valve at the entry. So we have an input here. So we have a flow I, the flow of the input measured in meter cube over second. So it is a volumetric flow. And here we have a tank with some liquid, okay, with a height h, which is controlled by the two valves. Now, Fi is seen as an input to the system, okay? And here we have the flow out, F. Also, it is a volumetric flow, meter cube over second. So here we will use the mass balance equation in order to write the differential equation that satisfies the height h. So we will apply the principle of continuity. It means the variation of the mass over time, okay, is equal to the flow in minus the flow out. So rho times V, it is mass because the V is the volume of the tank. Rho is the density of the liquid. So rho times V gives mass. Mass over second became a flow. So the variation of the flow will be the flow in minus the flow out. And here we have the flow are F and Fi are a volumetric flow. If we will multiply it by the density rho, it became it becomes now a mass flow. Okay, so the volume of this tank, it is the surface AC, which is supposed to be constant, times the height of the liquid. Okay, so H times AC will be the volume times the rho will be mass over second. Okay, so the variation of the mass, okay, is equal to the flow in minus the flow out. Okay, now if I don't have any variation of H, it means the flow in will be equal to the flow out, which is exactly the continuity, the well-known continuity equation. So AC is supposed to be constant and the density of the liquid is constant. So we can make rho AC outside the differentiation operator. And here we will have H times AC equal to Fi times rho minus F times rho. We will assume that the density there is no variation of the density of the liquid. So it is constant. So rho will be equal to rho I. And here we have rho from that side, so the rho will be simplified in both sides of this equation. And I will divide by AC. I will get dH over dt equal to Fi over AC minus F over AC. If we assume that the flow at the output is beta H, so here we will have H dot plus beta over AC H equal to a constant multiplied by the flow at the input side. And this is a differential equation with respect to H, okay, controlled by the input Fi. To get the response Ht, we will compose the Laplace transforms in both sides. So here we will have S H of S plus beta over AC HS equal to 1 over AC Fi of S. Okay, and then we will form the ratio HS over Fi of S. It means output over input. So we will have 1 over AC S plus beta over A, beta over AC, okay? Assuming that each of 0 is equal to 0. So the transfer function always is calculated when the initial conditions are equal to 0. This is an example of an RC circuit, and the objective here is to get the transfer function of this circuit. So the transfer function is defined as the ratio of V2S over V1 of S, where V1 of S, V2 of S are the Laplace transforms of V1 and V2. So here I will see now, using voltage division rule, that V2, okay, so V2 is what? It is the impedance of C divided by R plus the impedance of C times V1. It's like I have V1 and I have what? I have two elements in series and I have a voltage across the capacitor C. So the V2 reads as impedance of C, which is 1 over CS, which is this. This is the impedance of the capacitor, okay? So V2 will be impedance of the capacitor divided by R plus the impedance of the capacitor, okay? Or I will write the Kirchhoff voltage law minus V1 plus Ri plus the impedance 1 over CS times I equal to 0. And V2 is what? Is this current, okay, times the impedance of C, which is this. And then I can get the ratio V2 over V1 to be 1 over RCS plus 1. This is a little bit complicated circuit composed by a source of a current of value equal to RT, so it is time dependent, okay? And the objective is to get V2 over R. It means I will see V2 as output and I will see RT to be an input. We see now that the inductance, the inductor L, okay, and the capacitor C2, okay, they are in parallel. So I will call capital Z the impedance of the equivalent L parallel C2. So it is ZC2 parallel ZL. So the ZL, it is J omega L and it is LS. So the ZL will be LS and the impedance of the capacitor will be 1 over J omega C. Well, the C is the value of the capacitor. And it means that ZC will be 1 over CS. So here we will have 1 over C2S, and here we will have an impedance which is equal to 1 over C1S. Right, so I will put now Z to be the equivalent element here, which is ZL parallel of ZC2, okay, which is this value, and I will call it Z. And then I will see R1 to be in series with the equivalent element here, okay? It means it is R1 plus Z. And then I will apply the current division rule. So the common voltage between the elements that are in parallel. So elements that are in parallel is what? Is the source of the current, the capacitor, the resistance R2, and then I have one element here, which is R1 plus Z. R1 plus Z. So this is why I will apply the rule of current division. So the common voltage will be equal to the sum of the currents, Rs, divided by the sum of the inverse of the impedances. So here I have 1 over R2, and here I have 1 over ZC1, okay? And here I have 1 over R1 plus the equivalent element here, that we call it here Z. So this is why we have 1 over R1 plus Z. So this gives the common voltage across the elements that are in parallel. In the same time, V1 is here, and it is the same voltage across the resistance R2, okay? So now if I will replace this by one element, if I will replace these two elements by one element of impedance equal to Z, okay? So I will see V2 and V1 as a voltage division problem, okay? So I will solve for V2 to be the equivalent impedance Z divided by the sum multiplied by V1. So from here, okay, I can get V2 over V1. V2 over V1 is equal to this quantity. And V1 divided by R is equal to 1 divided by these terms, okay? So now if I will multiply the two ratios, I can get V2 over R, which is the product of this, times 1 over this term, which gives this transfer function. We see now that V2 as output, the R as input. So V2 over R defines the transfer function of the circuit where V2 is seen as output and R is seen as input. We can have also a transfer function between V1 and R, okay? We can get the transfer function between V1 plus V2 and R, okay? So we can define any transfer function that relates a measured variable to the input R. I will not solve completely this exercise, but I will give you a hint how to get the transfer function V0 divided by Vin. It means the voltage of the output divided by the voltage of the input. The simplest way is to define nodes, essential nodes. So here we have A to be an essential node. So I can write KCL, or the voltage node equation, at node A. What I have, we have this current plus this current plus this current is equal to 0, okay? So this current can be expressed in terms of the voltage Vn and Va. So this current, it is Va minus Vn divided by the impedance of this capacitor. This current, it is Va divided by R1. This current, it is Va minus V0 divided by the impedance of C. When we write this node equation, we will have three variables appearing: Vn, Va, and V0. So we have to eliminate the Va. So we need an extra equation. Taking into account that the current flowing here is 0, it means that the current which is flowing in R2 will be exactly this current multiplied by -1, okay? It means it is the inverse current. So the current which is flowing here, it is what? it is, if I will take this sense of the current, okay? So this current and this current have the same value, but they are in the opposite directions. So I can express this current as what? As Vin minus V0 divided by R2. In the same time, it is equal to the minus of this current. And the minus of this current is what? It is V0 minus VA divided by the impedance of this capacitor. With these two equations, we can eliminate VA, and then we can form one equation which is dependent only on V0 and Vn. When we have an equation which is only dependent on V0 and Vn, we can divide, okay, the equation by Vn, and we will form the ratio V0 by Vn, which is exactly the transfer function of this circuit. As a final example, I will treat now the model in time. So I will provide the time model of this mechanical system, and then I will show how can we get the transfer function that relates the input U to the output Y1. From the second law of Newton, that says that the mass times acceleration is equal to the sum of the forces applied to the system. So this is a system which is 2 degrees of freedom. So it has two displacement, yani M1 has a displacement Y1, and M2 has an independent displacement Y2. So the number of the degrees of freedom of this system is equal to 2. So we will have two differential equations that are coupled with each other, that they are linear with respect to the variable Y1, Y2, and the respective higher derivatives. I will start first by writing the Newton law to the mass M1. So what is this force? So this is a force related only to this spring K1. So this force, it is K1 times Y1, but its direction is in the opposite positive direction of Y1. So when we write the Newton law, we will write it with sign minus. This force is the damper force, and the damper force, it is a constant B times the speed. It means this force, it is B times Y1 dot. It means the first derivative of Y1, because the force of a damper is proportional to the speed, and it is in the opposite direction of the displacement. So if the displacement is like this, the force which is created will be in the opposite direction of Y1. So it is B Y1 dot, but it will be taken with sign minus because it is in the opposite direction of Y1. This force is related to this spring, okay? So I have a force from here and a force from here, okay? So the force which is here, it is the value of the spring K2 multiplied by Y2 minus Y1. So this force, it is K2 multiplied by Y2 minus Y1. Okay? And this force is related to this spring. So it will be K3 multiplied by Y2 minus Y1. This force and this force have the same magnitudes, but they are acting in an opposite way. So this force, as I said, it is K2 times Y2 minus Y1. So this one, it is the minus of this force. It means it is minus K2 times Y2 minus Y1. The same thing here. This force is equal to this force, but it is in the opposite direction. It means it has a value equal to K3, okay, Y1 minus Y2, or it is minus of K3 times Y2 minus Y1. The input U, it is an external force which is applied only on the mass M2. So now if I will write M1 times the acceleration, it means Y1 d dot, 2 dots, second derivative of Y1, equal to the sum of the forces. The sum of the forces applied to this mass is this force, this force, this force, and this force. And the mass M2 times Y2 d dot will be equal to U minus this, okay? So these are the whole forces, that are applied to the mass M2. So this is what we will write, assuming that all the parameters here are equal to 1, including the damper coefficient. So we will be left with the two coupled differential equations that are dependent on Y1 and Y2. How can we now have the transfer function that relates the input U to the output Y1? So I have now two differential equations. I will apply the Laplace transform in both sides, and I will apply here Laplace transforms to this differential equation. I will get the following. So I don't forget to put all the initial conditions are equal to 0. By applying the Laplace transform, and I will use the differentiation property for the differential to get these two equations that are coupled, okay? So we are seeing Y1 and Y2 in both equations. So I have a system of two variables, Y1 and Y2. I can solve these two system of equations as I have x1, x2, okay? It's like I have two variables to be found, okay? So when I will get Y1 and Y2, okay, they will be dependent on U. And then I can form the ratio Y1 divided by U to get the transfer function that relates the input U to the output Y1. I can get also the transfer function that relates the input U to Y2, okay, when I will solve this system of equation with respect to Y1 and Y2. I will leave you to get the detail and to solve for Y1 and Y2, and then form the ratio to get this